This conference will now be recorded.
Good afternoon, students. Last class, I started the stability analysis of finite side slopes. In that, I explained different methods used in stability analysis of finite side slopes. In the stability analysis of finite side slopes, we have friction circle method, Taylor's method, Swedish circle method, and Bishop's method. These four methods are used in the stability analysis of finite side slopes. Last class, I explained the friction circle method procedure in the stability analysis of finite side slopes. In that class, I explained to you the stability analysis of finite side slopes is conducted on the graph sheet in office. It is totally the drawing work. So in that stability analysis of finite side slope, we prepare the plan of the embankment, earth dam or canal in the graph sheet. Then we consider one imaginary failure surface. In that friction circle method, we consider arc of circle as the failure surface. Then we determine the forces acting on the soil wedge. That soil wedge is in between the side slope and the failure surface, the weight of the soil wedge, the mobilized cohesion force, and the reaction force. Then we prepare the force triangle. From that force triangle, we calculate the magnitudes of mobilized cohesion force Cm and also the reaction force R. By using that mobilized cohesion force Cm, we calculated the unit mobilized cohesion force, small cm. Then we find out the factor of safety of cohesion, Fc is equal to C divided by Cm. That is the friction circle method procedure. It is totally graphical approach. Then the next one is the Taylor's method. The second method of stability analysis of finite side slopes is the Taylor's method. This Taylor's method is similar to Kalman's method. In the previous classes, I explained that Kalman's method of stability analysis of finite side slopes. Almost in 2 or 3 classes, I explained that because it is an important concept. This Taylor's method is also similar to the Kalman's method. It is same as Kalman's method except some minor modifications. So this Taylor's method is graphical method and also mathematical procedure. Now in the today's class, I will explain this Taylor's method of stability analysis of finite side slopes. Then I will also explain what is that stability chart in this Taylor's method of stability analysis. In the semester examinations, the numerical problems in unit 2, in the semester examinations, the numerical problems in unit 2 will come from this Taylor's method. In the gate examination also, we have the numerical problems from this Taylor's method of stability analysis of finite side slopes. So please everyone go through this Taylor's method. It is similar to Kalman's method. So follow that Taylor's method in the class. Now, what is that Taylor's method of stability analysis of finite side slope? First, everyone check this diagram. Observe this diagram in the Taylor's method. If you remember, this diagram is similar to Kalman's analysis of finite side slopes. I explained this same diagram. So check the diagram. AB is the finite side slope. It may be the side slope of embankment, side slope of earth dam or side slope of canal. AB is the finite side slope with horizontal. The side slope AB making the angle I. It is similar to Kalman's method, same as Kalman's method. The Taylor's method approach is also same as Kalman's method. We discussed this diagram in the Kalman's method. I explained this diagram. So in the Taylor's method also, we consider the side slope AB making the angle I with horizontal. This is the finite side slope. Then H is the height of this side slope, vertical height. With this vertical, the side slope AB makes an angle of 90 minus I. Then we consider the failure surface AD in the diagram, in the plan. Here this AD is a plane failure surface, not the circular arc. In the friction circle method, we consider that failure surface AD as an arc of circle because in friction circle method, we assume the failure of the side slope is rotational failure. Whereas in the Taylor's method, we assume the failure of this side slope AB is a wedge failure. Since it is a wedge failure, in wedge failure, the failure surface is a plane failure surface, straight line. So in the Taylor's method, we assume the side slope AB subjected to wedge failure. So here the failure surface is a plane failure surface, that is AD. Consider this failure surface AD in the graph sheet. Let the failure surface AD with horizontal making the angle alpha. So in this diagram, the side slope AB with horizontal making the angle I. The failure surface AD with horizontal making the angle alpha. At the time of failure condition, this entire portion of soil, between the side slope AB and the failure surface AD is under failure. We call this portion of soil ABD as the soil wedge. So at the time of failure condition, the soil wedge ABD is subjected to failure. It moves in downward direction. We are going to discuss the failure condition of this soil wedge ABD. At the instant of failure, what are the forces acting on the soil wedge? In the Kalman's method, I explained the forces acting on that soil wedge. So check this diagram in the Taylor's method. At the condition of failure, the first force acting on the soil wedge is weight W. W is the weight of the soil wedge. To find out this weight W, calculate the area of this triangle ABD. Calculate the area. First find out this length AB. To find out this length AB, take this right angle triangle in the left side. To find out the length AB, take out this right angle triangle. In this right angle triangle, with respect to 90 minus alpha, 90 minus I. With respect to 90 minus I, H is the adjacent side, AB is the hypotenuse. So cos 90 minus I is equal to H divided by AB. Cos 90 minus I is sin I. So sin I is equal to H by AB. So this AB is equal to H divided by sin I. So this length of AB side slope is H divided by sin I. Take this length of the failure surface AD as L. I am explaining the calculation of weight W of the soil wedge. At the failure condition, the soil wedge is subjected to the first force weight W. We are going to discuss the calculation of weight W. To find out that weight W, first find out the area of this triangle ABD, the area of this triangle. So first we calculated the length AB. length AB is equal to h divided by sin I. Take this length of AD as L. Then check this point A. At point A, between the line AB, line AD, here this angle is I minus alpha. This angle is I minus alpha. Then according to geometry, the area of this triangle ABD, triangle area ABD is equal to half into length AB into length AD into sine I minus alpha. That is the area of this triangle or the soil wedge. So the area of this soil wedge ABD is equal to half into length AB into length AD into sine I minus alpha. What is this length AB? H divided by sin I. What is this length AD? L. So the area of this soil wedge A is equal to half into length AB H divided by sin I into length AD L into sine I minus alpha. That is this area of the soil wedge. Consider unit thickness of this soil wedge. In the particular direction, take the unit thickness. Then the volume of this soil wedge V is equal to area into unit thickness. What is that area? Half into h divided by sin I into L into sine I minus alpha into unit thickness. That is the volume. Let gamma is the bulk unit weight of this soil wedge. Take the gamma as the unit weight of this soil wedge. Then this weight W is equal to the unit weight gamma into volume. Volume is half into h divided by sin I into length L into sine I minus alpha. That is the weight of soil wedge W at the failure condition. This is first force. Then the second force is when this soil wedge subjected to failure, it is moving in downward direction on this surface AD. AD is the failure surface. At the failure condition, the soil wedge is moving in downward direction. At a downward movement, that is in failure condition, the soil wedge applies the force Cm on the failure surface in the downward direction. We call this Cm as the mobilized cohesion force. We call this capital Cm as the total mobilized cohesion force. Here in the diagram, in this diagram, this Cm is the force applied by soil wedge on the failure surface AD. Since this soil wedge is in downward movement, at the failure condition, the entire soil wedge is moving in downward direction. The soil wedge applies this force Cm on the failure surface AD in the downward direction. So the second force in the diagram is Cm, unknown force. We cannot find out this force Cm, but check the direction. The direction of Cm parallel to surface AD, so with horizontal, the force Cm makes the same angle alpha. Then the third force is at the condition of failure, the soil wedge is moving only in the downward direction parallel to failure surface AD. Please listen this carefully. At the failure condition, the soil wedge AD is moving in the downward direction parallel to surface AD. It is not moving. The soil wedge is not moving in the perpendicular direction to failure surface AD. There is no movement of this soil wedge in the perpendicular direction of failure surface AD. Since this soil wedge is not moving in the perpendicular direction, the third force, that is the reaction R, is acting on the soil wedge. So please listen this carefully. You might have studied in the engineering mechanics. If the surface prevents the movement of a body in a particular direction, then in that direction, the body applies action on the surface. then the surface applies the reaction on the body. That is there in the engineering mechanics. So here the soil wedge is moving parallel to failure surface AD, but it is not moving perpendicular to failure surface AD. So the failure surface AD applies the reaction force R on the soil wedge. That reaction force is acting in upward direction in soils. In soils, this reaction force from this failure surface on the soil wedge is always making some angle with this perpendicular direction. This dotted line indicates the perpendicular to failure surface AD. With the perpendicular direction, the reaction force R will make some angle indicated as phi m. This phi m is called the mobilized angle of friction. In soil mechanics, in geotechnical engineering, this mobilized angle of friction phi m is equal to phi divided by factor of safety. That is the equation. The mobilized angle of internal friction phi m is equal to phi divided by factor of safety. We call that phi as the natural angle of internal friction. Natural means in the borrow area, in the undisturbed condition, we must collect the soil from particular location, borrow area. Before the construction, before the excavation of that soil, the soil is in undisturbed condition. In that undisturbed condition, the soil will have one particular value of angle of internal friction, that is called the natural angle of internal friction phi. In the laboratory, we can calculate that value phi. In the geotechnical laboratory, we can determine that value phi. So from the borrow area, we can collect the soil samples, undisturbed soil samples. We test that undisturbed soil sample in the geotechnical laboratory. From that experimental investigation, we can find out the angle phi of that particular soil. Divide that angle phi with a factor of safety, either 1.5 or 2, you will get this angle phi m. So the reaction force R is making that angle phi m with this normal direction. So three forces are acting on the soil wedge at the failure condition. One is this weight of the soil wedge W. Next one is the mobilized cohesion force Cm. Please check this carefully. This Cm is the force applied by soil wedge on the failure surface AD downward direction. Since this Cm, since the soil wedge is applying the force Cm on the failure surface AD from Newton's third law, the failure surface AD also applies the same force Cm on the soil wedge, but in the opposite direction. Opposite means in the upward direction. I will show that later. So this soil wedge at the failure condition subjected to three forces: weight of the soil wedge W, the mobilized cohesion force Cm, and this reaction R. I hope you remember. You can write this capital Cm is equal to small cm into length of this failure surface AD L. So capital Cm is equal to small cm. Small cm is called the unit cohesion, the cohesion force per unit length into the length of the surface ADL. Three forces are acting on this soil wedge. So in the Taylor's method, please listen everyone. In the Taylor's method of stability analysis of finite soil slopes, first we consider the soil slope AB of the embankment, canal or earth dam. So in the diagram, the slope AB here, this slope AB is the finite soil slope. With horizontal, it is making the angle I. Then we consider the failure surface AD in the graph sheet. In Taylor's method, we assume the finite soil slope subjected to wedge failure, not the rotational failure. Since in Taylor's method, the failure is wedge failure, the failure surface AD is a straight line. it is making the angle alpha with the horizontal. Then the entire soil portion between the soil slope AB and the failure surface AD is subjected to failure. We call this soil portion as soil wedge. Just now I explained, at the failure condition, the soil wedge is subjected to three forces. One is the weight of the soil wedge W. Next one is the reaction force R. Third one is the mobilized cohesion force in the upward direction. So at the condition of failure, the soil wedge is subjected to three forces. Coming to this W calculation, I explained this in the Kalman's method. The same procedure we use in the Taylor's method also. Coming to the determination of W, the weight of the soil wedge. So first I calculated the area of the soil wedge ABD. The area of this soil wedge ABD is equal to half into length AB into length AD into sine I minus alpha. Length of AB soil slope is h by sine I. The length of soil slope is h by sine I. So the area of this soil wedge ABD half into h by sine I into L into sine I minus alpha. Then we calculate the volume. We assume unit thickness. We calculate the volume. So volume is equal to area into unit thickness. So this volume is half into h by sine I into L into sine I minus alpha. Take gamma is the bulk unit weight of soil. Then the weight W of soil wedge is the bulk unit weight gamma into volume. So here this weight W is half into gamma into this remaining portion h by sine I into L into sine I minus alpha. 1 by sine I is cosecant I. 1 by sine I is cosecant I. So this weight W is equal to the weight of the soil wedge. W is equal to half into gamma bulk unit weight into L into H into cosecant I into sine I minus alpha. This is the equation for the weight of the soil wedge ABD. Then the mobilized cohesion force capital CM. It is the total mobilized cohesion force that is equal to small cm unit cohesion, unit mobilized cohesion into length AD. Because this capital CM is acting on the surface AD, failure surface AD, the capital CM is equal to small cm into length L. So here we don't know the magnitude of this capital CM. It is unknown force. Mobilized cohesion force is unknown. We know only the direction. On the soil wedge, it is acting upward parallel to failure surface AD. Third one is the reaction force, this R. So from this failure surface, the reaction force is acting on the soil wedge. So check this diagram, please. We discussed this diagram in the Kalman's method also, the same diagram. So in the Taylor's method also, the soil wedge subjected to weight of the soil wedge W vertically downwards, the mobilized cohesion force Cm in the upward direction, the reaction R from the failure surface in the upward direction making an angle phi m with this particular direction. So the three forces W, Cm and R, these three forces are keeping the soil wedges in equilibrium condition, about to failure condition. When the soil wedge ABD is about to failure, three forces acting on the soil wedge W, Cm and R, they keeps that soil wedges in equilibrium condition. So the three forces W, Cm and R will form the force triangle. They will form the force triangle because the three forces are in the equilibrium condition. Now check that force triangle. Before going to discuss that force triangle, look at the three forces in the diagram. In that diagram, we know, please listen everyone, in the diagram we know only the direction and the magnitude of weight W. So this is only the known force. We know the direction and also the magnitude of weight W. Then we don't know the magnitude of force Cm. This is unknown force, but we know the direction. The direction is upward, parallel to failure surface AD, so with horizontal. The force Cm making the angle alpha. That is known only in the direction, not in the magnitude. Third force is reaction R. It is also unknown force. The reaction R is also unknown in the magnitude, but we know the direction. Direction is upward, making an angle phi m with this perpendicular direction. So out of these three forces, we know only the direction and the magnitude of force W. Then coming to this second force, we know only the direction of force Cm, but not the magnitude. Coming to third force, we know only the direction of reaction R, but not the magnitude. Now, how to draw the force triangle by using these three forces? Check that procedure. To draw that force triangle, you know that the triangle has three sides. To draw that force triangle, first take this weight W as one side of the triangle according to convenient scale. Like 1 centimeter is equal to 5 kilonewtons. If that weight W is 50 kilonewtons, then draw a vertical line, because W acting vertically downwards. Draw a vertical line. It is 50 kilonewtons. The scale is 1 centimeter is equal to 5 kilonewton. So the length of this vertical line is 10 centimeters. So on the white paper, first to draw this vertical line of length 10 centimeter representing the weight 50 kilonewtons on the solid wedge. The starting point, this is the starting point, this is the ending point. This arrow indicates the weight acting vertically downwards. Then from this starting point, draw a straight line. From this starting point, draw a straight line parallel to direction of force Cm, because we know this direction of force Cm. So from this starting point, draw a straight line parallel to direction of force Cm of some length. Of some length, draw a straight line parallel to direction of force Cm. Then from this second point, draw the another straight line parallel to direction of force R of some length. These two straight lines, this straight line from the beginning and the another straight line from this end, these two straight lines will cut with each other at this point. So at this point, the two straight lines are cutting with each other. Now check this triangle. In this triangle, one side, this is W. The second side, this is the second side. It is representing the force Cm, and this third side representing the force R. Indicate the direction on the second line in the direction of force Cm. Indicate the direction on the third line in the direction of force R. Then this length of the second straight line. The length of this second straight line is the magnitude of force Cm. The length of this second straight line is magnitude of force Cm. The length of this third straight line is the magnitude of reaction force R. So like that, in the Kalman's method, we can prepare that force triangle by using the force W, force Cm, and the reaction force R. Now coming to the angles in that triangle, last class I explained in the Kalman's method. Check that angle between W and Cm. Between the forces W and Cm, we know that with horizontal, check this diagram here, with horizontal, the force Cm makes the angle alpha. So with horizontal here, the angle is alpha, and here the angle is 90, so this third angle is 90 minus alpha. So between the forces Cm and W, here the angle is 90 minus alpha. Already I explained this in the Kalman's method. Then between the force R and force Cm, the angle is 90 plus phi m. I hope you remember that angles between the forces. I explained them already in the Kalman's method. Check this diagram. So between the force Cm and W, here this angle is 90 minus alpha. Then between the force R and force Cm, between the force Cm and this perpendicular, this angle is 90 plus phi m. So between the force R and force Cm, this total angle is 90 plus phi m. So coming to the force triangle, between the forces Cm and W, the angle is 90 minus alpha. Between the force Cm and the reaction R, the angle is 90 plus phi m. So this third angle. This third angle is equal to 180 degrees minus 90 minus alpha minus 90 plus phi m. So this third angle comes to alpha minus phi m. So in this force triangle, the first side W, the second side reaction R, the third side mobilized cohesion force Cm. Then we also know these angles in this force triangle. Apply the sine rule in this force triangle. Apply the sine rule. According to sine rule, the force Cm divided by the sine of opposite angle, phi alpha minus phi m. Sine rule, according to sine rule, force Cm divided by sine alpha minus phi m is equal to force W divided by sine of opposite angle, sine 90 plus phi m is equal to force R divided by sine of opposite angle, sine 90 minus alpha. That is called the force triangle, the sine rule in that force triangle. So check that sine rule in the diagram. Force Cm divided by sine alpha minus phi m is equal to, that is opposite angle. If I consider this force Cm, to this force Cm opposite angle is alpha minus phi m. To this force W opposite angle is 90 plus phi m. To this force R opposite angle is 90 minus alpha. So as per the sine rule for this force triangle, force Cm divided by sine alpha minus phi m is equal to force W divided by sine 90 plus phi m is equal to force R divided by sine 90 minus alpha. Take the first two terms in the sine rule. The first term is Cm divided by sine alpha minus phi m is equal to the second term W divided by sine 90 plus phi m. Take those two terms only in this force triangle sine rule. You will get the equation as, so force Cm divided by sine alpha minus phi m is equal to force W divided by sine 90 plus phi m. Simplify this equation first. Capital Cm divided by sine alpha minus phi m is equal to W divided by sine 90 plus phi m is cos phi m. Sine 90 degrees plus phi m is cos phi m. Bring this W to the left side. Sine alpha minus phi m to the right side. This equation becomes as, so bring this W to the left side. Sine alpha minus phi m to the right side. You will get this equation as capital Cm, that is the total mobilized cohesion force. Capital Cm divided by W is equal to sine alpha minus phi m by cos phi m. So from that force triangle, by applying the sine rule, we got that equation 3. Capital Cm divided by W is equal to sine alpha minus phi m divided by cos phi m. Please remember, capital Cm is called the total mobilized cohesion force, that is equal to small cm into length of the failure surface AD. Capital Cm is equal to small cm. Small cm is called unit cohesion. The cohesion force per unit length, that is small cm, into AD. AD is the length of the failure surface. Length of the failure surface, that is L. So capital Cm is equal to small cm into length L, and we know this weight W of Silvage ABD. Weight W is equal to half into gamma into L into H into cosecant I into sine I minus alpha. This is the equation of the weight W. So in the left hand side, capital Cm is equal to small cm into length L divided by the weight of the side wedge is half into gamma into L into H cosecant I into sine I minus alpha. Now on the left side, cancel this length L. In the numerator and denominator, cancel this length L. Then in the left side, keep this Cm by gamma H only in the left side. Keep that Cm by gamma H only in the left side. Bring this entire denominator to the right side. Bring the remaining denominator. What is the remaining denominator? Half into cosecant I into sine I minus alpha. Bring this entire denominator to the right side. Keep the right side observation, please. In the right side, sine alpha minus phi m by cos phi m. 1 by cos phi m is secant phi m. So in that right side, you can also write this right side as sine alpha minus phi m into secant phi m, because 1 by cos phi m is secant phi m. So this equation becomes as, I cancel this length L first. In the numerator and denominator, I cancel that length L. I keep this gamma H only in the denominator. I send this remaining terms. What is the remaining term? Half into cosecant I into sine I minus alpha to the right side. Now this equation becomes as Cm by gamma H on the left side. Cm by gamma H. This is gamma. This is H. Cm by gamma H is equal to, bring this remaining terms to the right side, half into cosecant I into sine I minus alpha. Then already in the right side we have sine alpha minus phi m, and 1 by cos phi m is secant phi m. So this equation changes to this equation 5 form. We just modify this above equation to get this equation 4. So in the left side, we cancel this length L first, and in the left side, we consider only Cm by gamma H, and we send the remaining terms to the right side. This equation becomes as Cm by gamma H is equal to half into cosecant I into sine I minus alpha into sine alpha minus phi m into secant phi m. This is the equation 4 in the Taylor's method. If you remember correctly, we prepare that same equation 4 in the Kalman's method also. In the Kalman's method also, we prepare that same equation 4. The same procedure is followed in the Taylor's method of stability analysis of finite side slopes. So whatever the procedure we discussed, in the Kalman's method, the same procedure is adopted in the Taylor's stability analysis also. So that equation 4, what that equation 4 we got in Taylor's method, we have that same equation 4 in the Kalman's method also. The same equation we discussed in Kalman's method. Now in the Taylor's method, we call this Cm by gamma H. This Cm by gamma H, I hope if you remember, in the Kalman's method also, we call that Cm by gamma H as stability number Sn. In the Kalman's method, please remember that in the Kalman's method, we call that Cm, small cm by gamma H in the Kalman's method as the stability number Sn. In the Taylor method also, we consider Cm by gamma H as the stability number, but it is called Taylor's stability number Sn. So in that equation 4, the left hand side, small cm, that is unit cohesion, unit mobilized cohesion, small cm by gamma h is called as the Taylor stability number Sn. Please check this equation. Sn is equal to cm by gamma h. Here this Sn is called the Taylor stability number. So up to this Sn cm by gamma h, the procedure of Taylor stability analysis is same as the Kalman's stability analysis. But the Taylor's conducted, he is a geological engineer. Taylor is a geological engineer. He conducted a lot of experiments in finite soil slopes based on that experimental observations. So many experiments Taylor conducted in finite soil slopes. Based on that experimental results, Taylor prepared tables and graphs to find out the stability number Sn. Whereas in that Kalman's method, we don't have those tables and graphs. We don't have the tables and graphs in the Kalman's method to find out the stability number Sn. But Taylor conducted a lot of experiments in finite soil slopes. Based on the experimental observations, Taylor prepared tabular forms and also graphs to find out the stability number Sn of finite soil slopes. So, based on the experimental results, Taylor prepared the charts and also the tabular forms. So, in that chart, he found out the relation between the angle of internal friction phi of the soil and the stability number Sn. In the tabular form, he prepared the relationship between the height of the soil slope and the stability number. So like that, based on that experimental results, Taylor prepared the tabular forms and also charts, graphs to calculate the stability number of finite soil slopes. Those are called the stability charts. The Taylor stability number graphs are called as the stability charts. I will show you those tabular forms and charts in Taylor's method of stability analysis. These are all the tabular forms. So please everyone look this diagram in the cell phone screens. In the Kalman's method, we were not discussed these tabular forms because Kalman does not propose this type of tabular forms, whereas Taylor, based on the experimental results, check this first tabular form. So in that first tabular form, based on the soil slope angle, based on the I is the angle made by soil slope with horizontal, based on the soil slope angle and based on the angle of internal friction of the soil. So in this tabular form, in the vertical direction, we have the finite soil slope horizontal angle I. In the horizontal direction, we have the angle of internal friction of the soil. So by knowing the angle of the finite soil slope with horizontal and the angle of internal friction of soil used in that soil slope, we can calculate this stability number Sn. So by knowing this phi value and by knowing this I value, I means the angle made by soil slope with horizontal, phi is the angle of internal friction of the soil. So by knowing this phi value and by knowing this I value, you can find out this Sn, Taylor stability number, from this tabular form. Whereas in the Kalman's method, we don't have this type of tabular form. And the second table is again based on the angle of soil slope with horizontal I. Then here we consider the depth factor df. Dear students, I explained in the base failure the depth factor. df is equal to h plus d divided by capital H. Please remember that in the last classes, I explained the failure of the finite side slope, phase failure and base failure. In the phase failure, we have slope failure and toe failure, and in the base failure, we have the depth factor df. In finite side slopes, the depth factor is equal to h plus d divided by h. So by knowing the height of the side slope and the depth of the hard stratum from the bottom of the embankment D, we can calculate the depth factor of that embankment. df is equal to h plus capital D divided by capital H. So by knowing the depth factor of the earth dam or embankment, and by knowing the side slope of the embankment or earth dam, we can find out this Taylor stability number. So in the Taylor's method, we have, this is the graphs. Taylor proposed these graphs for the finite side slopes to find out the stability number by knowing the angle I and the shearing angle phi. Like that, the Taylor proposed based on the observations, based on the experimental observations. Taylor proposed the tabular forms and also these charts. We are calling these graphs as stability charts. So this type of charts and graphs are not available in Kalman's method. Only in Taylor's method, we have this tabular forms and charts. By using them, you can calculate this pattern of this stability number Sn. So in the Taylor method, the stability number Sn is equal to Cm by gamma h. In this equation, Sn is called Taylor stability number. Small cm unit mobilized cohesion, gamma unit weight of soil, h height of the soil slope. Please remember the factor of safety of cohesion Fc is equal to, factor of safety of cohesion is equal to small c natural unit cohesion divided by small cm unit mobilized cohesion. This is the equation of factor of safety of cohesion Fc. Fc is equal to small c unit natural cohesion divided by cm unit mobilized cohesion. That is the ratio. The natural unit cohesion small c divided by the unit mobilized cohesion cm is called factor of safety of cohesion Fc. From this equation, you will get this cm. The mobilized cohesion, unit mobilized cohesion cm is equal to c by Fc. So from this equation, small cm is equal to c by Fc. Substitute this cm in the stability number Sn. Sn is equal to cm by gamma h. But this cm is equal to c by Fc. So this Sn becomes as the Taylor stability number Sn is equal to c by Fc into gamma h. This is the another equation. Just we modify this small cm as c by Fc. So the Taylor stability number Sn is equal to c unit natural cohesion divided by Fc into gamma h. Then the another modification of this equation phi. Another modification is if the height of the side slope increases, if the height of the finite side slope increases at one particular height, the side slope is about to failure without changing the angle I. Without changing that angle I, if the height of finite side slope increases at one particular height, the finite side slope subjected to failure, that is called the critical height Hc. Critical height is the vertical height at which the finite side slope is about to failure, that is called the critical height Hc. Then by knowing that critical height Hc and the available height h, h is called available height of the finite side slope. Hc is called the maximum height of the side slope at which the side slope is about to failure. By knowing that maximum height, it is also called critical height Hc. and the available height h, we can also define the factor of safety of cohesion in Taylor's method. Fc is equal to hc by h. hc is the maximum height at the time of failure. H is the available height. So the factor of safety of cohesion in Taylor's method is hc by h. From this, the height h is equal to, here we have this height h. So bring this h to the left side. Fc into h is equal to hc. We have that Fc into h here. In the equation 5, we have that Fc into h. This Fc into h is hc. This is the maximum critical height. So this equation 5 is also written as. So check this stability number in the Taylor's method. The Taylor stability number Sn is equal to, first I explain Cm by gamma h. Actually, this is the Taylor stability number Sn, Cm by gamma h. But Cm is equal to C by Fc. So that Taylor stability number Sn is also equal to C divided by Fc into gamma h. But Fc into h is the critical height hc. So that Taylor stability number Sn is also equal to C divided by gamma into hc. So like that, that Taylor stability number is having three equations. Sn is equal to Cm by gamma h. It is equal to C divided by Fc into gamma h. It is also equal to C divided by gamma into hc. These three are the equations of Taylor stability number. Then while solving the problems, please listen everyone, while solving the problems, in the numerical problems, they might have given the C value. In the numerical problem, they will give this gamma value. They will give the slope of the, they will give the angle of the side slope I. Please listen everyone. In the numerical problem, sometimes they will give the unit natural cohesion small c value. They will give the bulk unit weight gamma value. They will give the angle of side slope with horizontal I value. They will give phi value, that is angle of internal friction phi. And in the numerical problem, they will ask this hc height. What is the maximum height of the side slope at the time of failure? So please listen everyone. In the numerical problems, they will give small c, they will give gamma, they will give I, angle of side slope with horizontal, they will give phi, and they will ask the hc value. To solve that problem, to find out this height hc, first you must know the stability number Sn. Find out the stability number Sn from this tabular form. Since in the numerical problem, they given this I value and also they given this phi value. For example, if the angle of phi is 20 degrees, if the angle of I 45 degrees, from this tabular form, at I 45 degrees and at phi 20 degrees, Sn is 0.062. That is the stability number, Taylor stability number 0.062 Sn value when the angle phi 20 degrees, angle I 45 degrees. So 0.062. Substitute that 0.062 in this equation Sn. From the tabular form, we found this Sn 0.062. You know C value in the problem. You know gamma value in the problem. Calculate this height hc. So like that, in the numerical problems, we can use the Taylor stability charts and Taylor tables. So this is the Taylor stability analysis of the finite side slopes. Taylor stability analysis of the finite side slope. Dear students, if anybody is having doubts in this Taylor stability number, stability analysis, you please discuss with me. Any doubts, students, in the Taylor stability analysis? You please discuss with me. It is the same as Kalman's method. Taylor method is almost same as Kalman's method. But in the Taylor method, we have the support of the tabular forms and the graphs to find out the stability number Sn. That's only the difference between the Taylor method and the Kalman's method. Remaining procedure is same, both are same. So if anybody is having doubt about this Taylor stability analysis, you please discuss with me. Lateral entry 119, are you there in the class? Lateral entry 119. He switched off the mic. So I think he is sleeping. And one more, that 118 KB. So he is the transferred student, I think. Sri Krishna or Sri Kishore, whatever. He is there in the class. Lateral entry, that is rejoined, that is transferred students from MBA, NBK or IT. He is there in the class. So he also switched off the mic. Not the mute, unmute condition, not the mute condition. Totally, he switched off the mic. Harish, regular 106. Harish, are you there in the class? Regular 106. Harish, are you there in the class? And lateral entry 107. Out of order. Not there in the class. Totally switched off. Might be sleeping. Okay. And regular 156. So only for attendance purpose, you people are joined in the class. Regular 156 also totally out of the station, and some more. Regular 137 totally out of coverage area. 137. So these students remaining are all there. Remaining all are in the class. Some students totally just entered into the class, switched off the mic, then they are doing their business. Okay, it's up to you. At least for few students, if my involvement is helpful, I am happy. Okay, students, if anybody is having the doubts, you please discuss with me. Otherwise, you please leave from the class. Please join the next class. Please leave from the class, students.